Okay, we'll look at the first couple of steps of reducing this matrix to its, actually we're going to reduce it just to its upper triangular form. And we'll see what that means in a minute. Okay, so, well actually here's upper triangular form, so let's just refer to that. It means that all of your non-zero elements are on or above the diagonal, and below the diagonal you have only zeros. Now this is just a 2 by 2 matrix, so you're just going to have 1 0 here. But if you have a larger matrix, well, here are a couple of examples in a 3 by 3 matrix. You don't have to worry about what we were doing here, we'll get to that quickly. But you see that the X's stand for, and I was just too lazy to draw asterisks. Actually, I was running out of chalk. And these are to be regarded as asterisks, and you see you have asterisks on the diagonal, but above the diagonal you have only zeros. Okay, that makes this matrix lower triangular. Here, well actually, yeah, you've got another lower triangular matrix. If all your zeros were below the diagonal in these three positions here, then you'd be an upper triangular matrix. That's a very simple idea, and we can see that this is an upper triangular matrix. To achieve the upper triangular form, and incidentally, you don't have to have a 1 here to get upper triangular, but we're used to getting a 1 here because it often makes it easier to get the 0. And we understand the matrix reduction process, so I can refer to that. So, starting with this matrix, we multiply the first row by 1/3. That's all we do. Okay, well, if we do that to the identity matrix, we get this elementary matrix. The identity matrix, remember, is your 1, 0, 0, 1 matrix. If we multiply the first row, which is 1, 0, by 1/3, this is what we get. Our second elementary matrix we get if we take the identity matrix, and we did this in class previously. Well, let's see what our next operation would be. Once we have the 1 here, we add -5 times the first row to the second, and we're going to get our 0 here. And at that point, we're in upper triangular form. Okay, well, if we add -1 times the first row of the identity matrix to the second row, this is what we get. So this is our second elementary matrix. Now I've got inverses of elementary matrices that I'll talk about in a minute, but let's just see what we have from the elementary matrix. Okay, well, as we've seen, if we multiply this matrix, which is obtained by multiplying the first row of the identity matrix by 1/3, if we multiply this matrix on the left by this matrix, which is on the right, we do get the 1 here. And we're going to get a 2 here, and the 5, -2 are going to stay there. So the first thing we want to do to reduce it, to reduce this matrix, is multiply it by E1. Okay, well then, if we multiply it by E2, that's going to have just the effect of adding -5 times the first row to the second. We've seen that, you can check it out. That's what will happen. So, we start with this matrix, we put this matrix on its left and do the multiplication. Then we put this matrix on the left and do that multiplication to the matrix that we got. That's the same as doing, starting with A, multiply by E1, and multiply that result by E2. And that will get you to this form. You can check that and you should verify it. So, we can say that E2 times E1 times A equals U, where U is an upper triangular matrix. If the matrix is reducible, then, well, yeah, we can always do this, okay? Now, this means, of course, if E1, E2 times A equals U, then what does A equal? Well, if we multiply both sides of this equation by E2 inverse, the E2 times E2 inverse will become the identity, and the identity times E1A is just E1A. So E1A will be E2 inverse multiplied by U. Then we multiply both sides by E1 inverse, and we end up with just A. Multiply this side by E1 inverse, well, it was E2 inverse U, now it's E1 inverse E2 inverse U. So, if you follow that, and you should, because we did this kind of in detail, wrote out details previously, the matrix A is E1 inverse E2 inverse U. Now you got to have the order correct, okay? So if we multiply E1 inverse E2 inverse by U, that's the same as multiplying E1 inverse E2 inverse by E2 E1A. You see that the E2 inverse would be right next to the E2, so that E2 inverse and E2 would give us the identity, which multiplied by E1 just leaves us E1, and that leaves us E1 inverse next to E1. That's going to give us the identity times A, and the identity times A is just A, so this is what we get. So that all verifies it, and you can refer back to where we did a much longer, well, four-step reduction, and you know, see how we treated those matrices. You should be pretty well familiar with that. The videos have been posted, and hopefully you've reviewed it. Okay, so I say this is a way cool thing. Now, way cool, something that came up before most of you were born, but it still seems really cool and modern to me. Not really. I'm dating myself by that. Okay, but I want to draw your attention to the fact that this is really kind of profound. And what's really profound about it is that E1 inverse, E2 inverse is a lower triangular matrix. Now, we haven't proven that. I'll explain why that is, but this is it. E1 inverse times E2 inverse is lower triangular. So what we have now, A is equal to this product, which is a lower triangular matrix that we'll call L. In other words, E1 inverse, E2 inverse is what we're going to call L, times U, which we know to be upper triangular. Okay? Again, L is E1 inverse, E2 inverse. Now, how do we know that that's a lower triangular matrix? Well, E1 is lower triangular. That is, above the main diagonal, you have only zeros, so it makes the matrix lower triangular. Doesn't matter if there's a zero here, it's still lower triangular. It's also upper triangular, but we don't care about that. It's lower triangular. That's what we need in order to figure this out. Okay, E2 is clearly a lower triangular matrix. The only zeros are above, well, above the diagonal you have only zeros. Okay? And if you multiply two lower triangular matrices, you get a lower triangular matrix. Now that's what I was doing down here. So for a 3x3 matrix, the worst case you would have would be where you have, well, okay, a lower triangular matrix has to have zeros here for 3x3, and of course another lower triangular matrix would have zeros here. So these numbers, these x's or asterisks, stand for completely, you know, they can stand for any numbers. And they, you know, the x's over here or the asterisks don't stand for the same things that they do over here. At least they don't need to stand for the same things. They could, but in general we don't assume that they do. Okay, so this is what it looks like to multiply two lower triangular matrices. Now, let's look at what happens when we multiply the first row by the first column. Well, yeah, nothing too spectacular. The only number other than zero we have here is whatever number is in this position, and that's going to multiply this, and then these two zeros will multiply these, just give us zero. So in the first position, the 1, 1 position of our product matrix, we just have this times this, which is just some other number. Okay, well that's okay. Now, if we multiply this row by the second column to get the number that goes in the first row and second column of our product matrix, what happens? Well, this is going to match this is going to match this is going to match this. Well, this matches this, but this is zero, so that's going to give us zero no matter what this is. And this matches, this is matched with this is then matched with zero, so when we multiply we're going to get zero, and this is matched with zero, we're going to get zero. So we get zero in the first row, second column. Same thing for the first row, third column. The only non-zero number we have in this row is this one, and it's multiplied by the zero that we have here. So our first row will consist of some number, which might or might not be zero, it doesn't matter, but then two zeros. So we're going to have the two zeros we need in the first row to give us upper triangular form. then all we got to do is verify that we're going to get a 0 in this position of our product matrix. And that's the second row, third column. If we multiply the second row by the third column, look at what happens. This is matched with 0, this is matched with 0, and this is matched with 0. So the product of the second row, third column is 0, and we'll have a 0 in the second row, third column, and that proves, or that at least demonstrates why when you multiply two lower triangular matrices, you get a lower triangular matrix. Now you'd have to do a inductive proof or something to verify this for larger matrices, but it's clear that it's going to work out, just from the pattern that we see here, if you think about it a little bit. So I haven't done a rigorous mathematical proof. I've just demonstrated for a general looking pair of lower triangular matrices that it has to work out for 3 by 3s. Take my word for it, it works out no matter what. So this is always going to be lower triangular. So now we will have decomposed A into a lower and an upper triangular matrix. Okay, well, we want to see what good that is, and you know, we also kind of need to see what E1 inverse and E2 inverse are. We know E1 and E2. Well, I've written down E1 inverse and E2 inverse, but let's discuss how you get E1 inverse and E2 inverse. It's very simple.